Okay, today we're going to be talking about light emitting diodes and solar cells. So, last time we learned about diodes, and a light emitting diode or LED is a type of diode which emits light. So most diodes that we learned about before, when you have a superconducting material, mostly they use are based on silicon, but silicon diodes do not emit light. So to get a light emitting diode, we have to use a different type of semiconductor. So most widely, we use gallium arsenide. So it's GaAs. And if you were to look on the periodic table, that's a group 3 element combined with a group 5 element to make a 3,5 semiconductor. Now what happens is, when the electrons, let's draw a diagram to explain it. So this is our battery, and we connect the battery to our semiconducting material here, and this is our light emitting diode, which has the symbol. So you take your diode symbol, but this time you have two arrows to indicate that it's going to emit light. And let's get some other colours. We'll split down here, and this is our N-type, and this is our P-type. So we've got our holes here, and on this side we have our electrons. So as they come, the electrons move over to the depletion zone. They are going to fill up a hole, so it will enter into this hole. Now if we draw this as an energy diagram, so this is our valence band, and this is our conduction band, and we have our electrons here in our N-type, and they're moving along in this direction towards the depletion zone. And then here in the depletion zone we have some holes, and in our P-type we have our holes. So as the electrons come up here, they fall down to fill a hole. Let's put another one up here. Now as they drop down from the conduction band into the valence band, they're going to lose energy, and that energy is lost as a photon of light. And so as we know from previously, when we have our energy levels, and an electron jumps down from one energy level to the other, and there's that photon of light that's lost, we know that energy is equal to Planck's constant times frequency, and so the frequency is obviously related to the wavelength. So this drop here, this energy gap that's dropped here, determines the frequency of the photon used, and this gap here is determined by the types of material we use. So when we use gallium arsenide, the energy gap that is here will give us a red wavelength of light. So this is how we get our red LED. If we were to put, say, we can put other materials in the manufacturing process when we're making our semiconductors. So other elements in the LED result in different wavelengths. So by knowing what the energy drop's going to be for different types of elements, different types of semiconductors, we can choose and we can engineer an LED to give us a very specific type of light. So when we add nitrogen with phosphorus, we get orange and yellow light. If we don't use arsenic, we won't get green light. We'll get green light will be produced. Ideally, so at first, scientists wanted the primary colours. So green, red, and blue. Green and red are easy to manufacture, but blue was a problem. Blue LEDs weren't widely available until the 1990s, when they were able to perfect the manufacturing process. Now we have LEDs that are infrared. So if you've got a television remote control, that's got an LED that produces infrared light to send that signal to the television, and we can also have UV LEDs. Now, white LEDs are a problem because white light is many wavelengths combined. But we can now buy LED lights that you can just put into your to use as your main lighting in your house. And obviously these are white. We don't have red lights in our house. We use white light. So they've come up with a way of dealing with this. So what they do is, there's two ways. The white light LED. So one is you coat a blue LED, with a particular type of paint. So you coat the LED with special coating, and you do it with a blue LED, and that changes the wavelength of some photons. And the second one is you combine the three primary colour LEDs together, and when you combine red, green and blue, you get white light. Now I'm running out of room. So we need to remember that LEDs, just like all diodes, are sensitive to high voltage. So therefore LEDs are often connected in series with a resistor to limit the voltage. because if the LED gets overheated, it's going to burn it. It's going to break it up. It won't work. So, like an LED, we're now going to look at solar cells, which are almost like the opposite. So solar cells also rely on a P and N junction. Now, with LED, that drop in energy level from the conduction band to the valence band resulted in a photon being released. Okay, one of the differences between solar cells and an LED is that solar cells are silicon based. So let's look at how this works. So we have our solar panel here, and kind of in a grid system, and you've seen them on houses. And the light is obviously going to come on and hit these solar panels. Now I'm going to exaggerate the depth because that's where all the action is. So let's get another colour. So this is going to be our depletion zone. So on the top we have an N-type semiconductor, N-type silicon, and on the bottom we have P-type silicon. And here we have our depletions on our junction. So if we look at what's actually happening here, we have our depletion zone, and we have our, so this is our N-type, our P-type here. Now, we have our light coming in here, and this is photons. So now, what happens is, when the photon is absorbed, so the photon is, the photon is absorbed and then electrons are raised from the valence band. Thus leaving a hole behind. So here we have electrons being absorbed, and this leaves holes behind here. And that then means there's going to be a potential difference across the cell. So we call this the photovoltaic effect. And when we have a potential difference, this leads to a current. So now a single photon isn't going to create much of a current. So when we have these array of solar cells all together working, you're able to build up a sizable current that is actually usable. The output is always going to be DC. It's always going to give you a DC current output, which makes sense. The photovoltaic effect was first observed in far back as 1839 by Becquerel, who is famous for his work on radiation. And the first solar cell, so this technology was first put into use as far back as 1883. Was the time when the first solar cell was made, but obviously it wasn't a technology at that time that was they couldn't utilise it. They needed Einstein to come along, and he actually won a Nobel Prize for his work on the photoelectric effect. And it wasn't until 1954 that the Bell's Lab in America made the first modern solar cell, so and something that could be used. They were used in satellites in the 1960s. And our first, so if you've got a calculator, it's got a solar panel on it. This is that technology. Solar powered calculators were first made in the late 1970s. In 2007, the first solar powered flight was made, and in 2010, the largest photovoltaic plant was completed in Canada. And so photovoltaic plants, solar energy plants, are now something that are widely used in places which get a lot of sun. You can see large arrays, for example, in the Sahara Desert. And obviously the technology has been harnessed more and more as we see this with solar panels on people's houses. So I hope that helps.